right, hello everybody. Welcome to the first virtual SI session for CS 146. My name is Hassib, and I'm the SI for the first two sections in this class.
Hi everyone, my name is Shivanku and I am the SI leader for section 3 and 4. And both Hassib and I will be taking virtual SI sessions. These sessions will be will be held every alternate week on Fridays. And my apologies for the technical delay because I was told at the last moment that there's a room available and I had to run all the way from PC to some other building really far from PC. Yeah.
Okay, no problem. So let's get it started. So as far as this session, this is the outline. I just want to touch a little bit over the logistics of this session, how the sessions will run. Then that will take about 5 minutes. Then we'll jump into comparison between binary search trees and the 2-3 trees. Really the goal for that idea is to see why are we studying 2-3 trees to begin with. Like, is binary trees are not enough? Well, there is some technical issues that 2-3 trees will solve for us, and we'll go over that. Then the third idea, it will be it's written with a mistake here. It should say in-depth view into insertion in 2-3 trees. Shivanku will walk us through details of insertion and different scenarios we can run into when we insert into 2-3 trees. And for the last couple minutes, we'll just have some closing remarks and we'll wrap up this session. So let me start talking a little bit about the logistics of the session. So these sessions will be held like a dialogue. It will be a dialogue between me and Shivanku, and really the learning opportunity is like to listen to that dialogue. It's like the same way when you listen to people discussing issues. It's all you learn from just people discussing it. So that's really the goal here in the virtual SIs, since the interactions here are very minimal. We can't see you guys in person, then personal interactions are not present here. Also, what I will be doing is I'll be posing questions. You guys can always answer these questions in the chat. If I'm the one giving, or if I'm the one asking the questions, Shivanku will be looking at the chat and going through the answers, and also letting me know, giving me like some feedback of what's happening in the chat, because I can't see it while I'm doing my section. And other than that, that will be how the sessions will go. This is the first one. It will be an interesting experience, and from now on, it will get a little more comfortable, and I'll try to crack some jokes here and there because it might get a little dry. You're just watching a video. I'll do my best. This is probably the first time that I show my face on a virtual session. I guess that makes it a little more personable. But other than that, let's get started. So right now I'm going to start touching on start with binary trees and the problems that we might face in binary trees and I'm going to ease my way into the 2-3 trees. So to begin with, I just let me change to a different view so you guys can see what I want you guys to see. All right, right now you guys should see this website that says B-trees, and I want to go here. So just a side note for everyone, there's this website. It's very useful. It's if you open Google and you go San Francisco data structures visualized. It will pop. This link will pop up. And if you opened it, this is a website that will help us visualize a lot of the algorithms that we'll be going over. So if you just search that in Google, it's by University of San Francisco, or San Francisco University. And yeah, once you search out for Google, you get this list, and each one of them is a way to to visualize algorithms. So that's a really big resource. We'll be using this in the virtual sessions quite often. So that's just a side note. Then from that page, I will be able to navigate to binary search trees, and I will start from here. So binary search trees, we all we took it in the beginning of the semester, and we probably got bored of it a little bit because we talked too much about it. But what I'm gonna try to do is come up or produce an input that will give me like an ugly binary tree. So let me start with this. I'm gonna start building a binary tree, and I'm gonna insert a 2. All right. Then the 2 goes on the root, no big deal. Then let's say I want to insert a 4 right now. Does the 4, and that's a question, does the 4 go to the left of the 2 or the right of the 2, or it doesn't matter? Shivanku, you can always jump in on that.
Yeah, sure.
So the 4, where would it go, right or left?
So it should go on right because it's greater than 2.
Okay, then I expect it to go to the right, so I insert it, and the website tries to insert it for me, and definitely goes to the right. Then it's a binary search tree, so the next value that I want to insert is a 5. All right, so I want to put a 5 in this tree. Where should I expect it to go?
I think it should again go to the right of the 4 because in binary search tree, as the insertion happens, it will compare it to 2. Since it's greater than 2, it will go to the right. And now it will compare itself to 4. Since it's greater than 4, it will get inserted on right of 4.
Okay, let's see if we can trust you. I'm going to press insert. And indeed, it goes to the right of the 4. Yeah. Then I'm going to insert a 6. And following the same logic, it should go to the right of the 5.
Yeah.
Insert it. And it indeed goes to the right of the 5. Then I want to insert 8. And I insert it. And we have the same idea. Keep going down, and it's going to go to the right of the 6. Then I want to insert 9. All right. Then all I know is I'm using a binary tree, but I'm seeing something weird. Then I want to insert maybe a 1. So if I'm inserting a 1, where the 1 should go?
It should go on the left because since it's smaller than 2, it'll be the left child node of 2.
Okay, so it will go to the left child of 2. Let me give it a try. And yes, it goes to the left child of 2. Then the next number that I have is 12. Would the 12 go to the right side of 1, or would it go somewhere else?
It should go to the right side of 2 because it will start from 2 since it's greater than 2. Now
Okay.
it goes to 4. Since it's greater than 4, it goes to the right. And it keeps on traversing till it goes till the root node, the leaf node, which is 9. So it will get inserted to right of 9.
Okay, I'm gonna insert it, and indeed, it keeps going down. Then I have another number, which is the last number, which is 15, and I think we know what's gonna happen. But just look at the animation and look how long does it take to insert a 15. Like it goes 1 by 1 by 1 by 1, and it compares and calls well. Then it inserts the 15. Then I look at this tree and I go, this tree looks weird. It doesn't look like a tree. It looks like a data structure that we took before, like similar to it. And my question is, what does it look similar to? What is that data structure that looks similar to this, what's in front of us right now? And let's give like a couple seconds just to see the responses. So what do you think, Shivanku? What does it look like?
I agree with a couple of responses I can see on the chat. It looks like a linked list.
A linked list, it's like a very long vine in a tree. Uh, it looks like a linked list, yeah, and it's like the binary trees should give us pretty good performance, but what's happening is like it looks like I'm going through a tree and I'm like, this is not good. So this is a common problem when it comes to the binary search trees. It's the fact that one side of the tree could have a lot more elements than another side of the tree just because of the way we inserted numbers. We started with a 2, so we started with a small number. So if all the numbers we inserted after are bigger than the 2, they're just going to keep going to the right side. And if my numbers are kind of sorted, it will start giving me this like long list. And that's a problem because the performance for this is not that good. That means every time I want to insert the number, it's like I have to visit almost every number that I have to insert it. And this is there is a technical term for this issue. They call it that the tree is not balanced. And when the tree is not balanced, it will give us a bad performance for insertion, like the rest of the operations too, that's when the tree is not balanced. So, and that triggered the need for us to look for maybe a different data structure that will not have these problems. And that's when the idea of balanced trees came up. So scientists, whoever came up with these trees, they were like, we want a data structure where we don't have to deal with the problem that the tree is becoming more like a vine or more like a linked list. We want to come up with a data structure that doesn't have this problem. And they came up with a whole class of trees. They call them balanced trees. And that's what triggered the need for it. It's the need for balanced data structures. And now we have 2-3 trees, which is a balanced tree. And so what I'm going to do right now is I'm going to take this input that I tried, then I'm going to try putting it in the balance, insert it in a 2-3 tree, and see what type of structure we get. So here, I'm not really looking at the insertion. I'm looking more at, is the tree that it's going to get produced balanced or not? And is the problem that I faced in binary search trees solved or not? So again, we're going to be using the same website, but it's just a different link, and it will take us to this B tree page of the website. And to make this B tree a 2-3 tree, I just need to specify that my max degree is 3. And yeah, that'll be it. In this case, I will have a 2-3 tree, and let me try to insert the numbers. So let me insert the first one. That should be an easy one. The 2 should go to the root, just like a binary tree. I insert it and it definitely goes to the root. Now my question is, I want to insert 4. Where does the 4 go? Does the 4 go to the left of the 2, to the right of the 2, with the 2? What does everybody thinks? I'm trying to insert a 4 after inserting a 2. It's a 2-3 tree. So Shivanku.
Yeah, I can see a couple of responses and they are correct. It should go with the 2.
It should go with the 2. Okay, let me try to insert it. And yeah, it goes with the 2. Then the next item in my list is a 5. What should happen when I insert the 5 for now?
So a split should happen.
A split. Let's see. I insert a 5, it goes into new. It definitely splits, yeah. And here's the question that I want to ask everybody. Why does it split? I want to know why my root node split when I inserted that 5. Is it because the number is a 5, or is it because maybe a restriction that we have in these in the 2-3 trees?
Yeah, so the answer would be that there cannot be more than two values or keys in the same node. So since when you insert 5, there will be three keys in the same node. So it will call the split function and it will split.
Okay, so yeah, in 2-3 trees, we cannot have more than more than two keys in a node. Once we hit 3, that's the indication of uh, of splitting. Yeah, once we hit more than 2 keys or 3 keys in a node, that's the indication that we're gonna split. All right, that's nice. Then the next item on my list is a 6. So where should the 6 go?
It should go with the 5 node.
Are you sure?
Yeah.
Okay, let's see. So I tried to insert the node, it goes into the 4, then it compares, and it definitely, yes, it goes to the 5. And it goes next to the 5, and specifically to the right of the 5.
Yeah.
And why did it go to the right of the 5?
So the reason for that is that insertion is so it is behaving like a binary search tree, but a balanced one. So insertion in binary trees is intuitive. So every time we are trying to insert something, it is on its own trying to balance the thing. So what I mean by that is that if we have another key which goes with 6, let's say if you have 7, and if it was supposed to split, at all times it will have a value which is greater than that on its right and a value which is lesser than that on its left, so that
Okay, so it's like
yeah.
maintaining some type of property that is similar to the
Yeah.
binary trees, bigger or less for the children, but we expand that property to 3 children and 2 children, depending on the situation. And as far as the keys inside the nodes, they should be sorted in general. So that's like specifically the reason why the 6 would go to the right of the 5 versus the left of it. Okay, so my next item on the list is a 7. I'm going to insert a 7. Okay. And I should have asked the question, but I did not ask it. So let me ask this. Why did it split? Why that bottom node split? I think we might know the reason, but I want to hear it again. Why did the bottom node with the 5 and 6 and 7 split?
Yeah, I can see responses in the chat that because it has on when you insert 7, now that node had 3 keys, so now it had to split.
Okay, so it's like the notion of being full, or the notion that, oh, it has a maximum number of keys that is 3.
Mm-hmm.
And we cannot have that. We have the maximum number should be 2, so we have to split. So this is the resulting tree that we got, and we have to pay like a close attention here, is that we have the property of a heap, but we're expanding it to the fact that we have 3 children. So like the 2 is less than the 4, so it goes to the left of the 4. The 5 is more than the 4 and less than the 6, so it goes to the middle, goes as the middle child. And the 7 is more than the 6, so it goes to the right. So more or less, it's like the same thought when it comes to binary trees, that the left child should be less than the parent, and the right child should be more. Here is just we have 3 children, and we have to take the fact into account that there's 2 keys, and the children should follow into the range of those 2 keys, or yeah, inside the range specified. Okay, so we have this tree so far. Let me insert my next item. It's an 8. So where should the 8 go?
To the right of 7.
Okay, to the right of
As
7.
in along with the 7. Yeah.
Okay, it goes next to the 7, I
Next to
guess.
7. Yeah.
Then my next item is a 9. So I insert a 9. We saw something interesting happen right now. Our level of the tree increased. And if we were paying attention, why did we end up increasing the level of the tree? I know that the bottom node was full, so it ended up sending or splitting and sending one more item to the root. But why did we end up getting a new uh, a new level?
I just wanted to point out some people wanted to see the animation again.
Okay.
So can you please pause the animation? It's at the bottom. It says pause,
Mhm.
and you can click step back so that it is like more visual.
Okay.
You can pause it before doing the insertion,
Mhm.
and yeah, click it. And every time and now you insert, and every time you just need to click step forward. So
Okay, I see.
yeah.
So again, I'm trying to insert a 9. I insert it,
And now you need to click step forward.
then skip forward.
No, not skip forward, step forward.
Okay, so I'm trying to insert a 9. The 9 goes to the root.
No, step forward. The,
Oh,
the the one next to play, the one which is on the right of play. Yeah,
oh,
this one.
I see. Okay, okay.
Yeah,
Then I'm trying to insert a 9. I insert it, then it goes to the root.
it checks.
It starts at the root, I
Yeah.
guess. It compares, it figures out that the 9 should go to the right of the 6. So we go to the right of the 6. Now we're inside the node that is right to the 6. Also, keep in mind that the number we're trying to insert is a 9. So while we're at this node, we know that the keys in the node should be sorted. So the 9 should sit next to the 8. Let's see what happens. And it definitely sits next to the 8. But now we have this condition where the node has 3 keys, and we don't want that. And we can see that signified here by this message: node now takes too many keys. So what will happen? We know that's a split is going to happen, and it sends the 8 up. Now we have a unique situation where the node has 4 children. I have 3 keys. Again, that's the same issue as we're having 2 more keys at the root. So what's going to happen? It's intuitive. We have to split. So we split the root, and the middle key comes up, and the 4 children get divided to the left and the right in their order to the side keys of the root, which were the 4 and the 8. So we can notice a unique situation here is that we ended up increasing the level, but that's something I want to leave until Shivanku touches on it in more detail. The idea here is we're trying to detect is 2-3 trees solving our problem of imbalanced trees. So that was the insertion that happened. Then I'm gonna start inserting my next item, which is a 12. And the 12 should go somewhere in the bottom. And I'm just gonna play it. Okay, it goes next to the 9. Then my last item to insert is a 15. I insert it, and it finishes insertion. So this is the tree that we have. And here what I wanted to make clear to everybody is just like to see the comparison between the 2 trees. So this tree here, it has, I want to ask, how many levels does this tree have?
I can see some responses which are saying 3 levels.
So this tree has 3 levels. Okay, that's nice. I inserted maybe a bunch of 6 or 7 numbers into my 2-3 tree and ended up producing 3 levels. Okay. How many levels does my binary tree has? I want to count it too, actually.
I think it's 8.
Okay. So yeah, my binary tree has 8 levels. It's the same numbers, but it has 8 levels. For this one, it has 3. And my question right now, which one is better for when it comes to performance in this specific situation? Is it the 2-3 tree or is it the binary? What do you think, Shivanku?
So it should be the binary tree because the time it will take for insertion to take place will be much less.
The binary tree?
No, the B trees.
Okay, okay. Then which is the 2-3 tree, exactly. Yeah, so like since we have 3 levels, we only need to go 3 levels down to insert something. But when it comes to the binary tree, it depends on the value that we insert. We might end up going 8 levels to try to insert something. And that's the benefit that we get from the 2-3 trees. Yeah, that's the benefit that we get with the 2-3 trees. It's less levels, it's more balanced, although we have the same input, we see here with the binary tree that we got a long vine, but with the 2-3 tree, it's more balanced. I have somewhat the same number of items toward the right and the left, and that kind of compressed my tree a little bit and made it more efficient for the operations that I'm going to do on it. So this is the point of this section this is why we're learning 2-3 trees. Those are balanced trees. They're balanced tree data structures, and they will yield us performance benefits regardless of the input that we have. So here in the binary trees, depending on our input, we might get this situation, but in the balanced trees, it really does not matter. So it's like one thing that we don't have to worry about anymore when it comes to the trees is I don't have to worry about the input, because if I'm using 2-3 tree, it's guaranteed that this tree is going to be balanced. It's not going to skew like the binary trees, and that's the benefit that we get, and that's why we're learning it. Yeah, it's something important to learn. Balanced trees are very useful. Okay, so I'm gonna leave it from here, and Shivanku's gonna take over, and he's gonna show us an in-depth view onto the insertion into 2-3 trees.
There's this two particular things I wanted to cover besides what Hassib talked to you guys about. So I wanted to take this tree as an example, and let's see what happens when we insert 60. And let's pause it and let's take a few steps back. So before I inserted 60, I had 30 as my root and 20 is towards its left, and I have 40 and 50 as one node towards the right of 30. So there are 2-3 things I want to point out. The first thing is that at all times, everything on the left of 30 is smaller than 30 and everything on the right of 30 is greater than 30. I know this sounds obvious because we know binary trees and we know this concept, but this becomes really important when we take the next step, like when we are trying to insert 60. Because when we insert 60, so it goes to 30, it checks, okay, it's greater than 60. So now it goes to this level of 40 and 50, and it tries to get inserted at this level, which is like this. Since this node now has 3 keys, so I wanted to ask one important thing to you guys. So what do you guys think, that 40 and 60 go a level down or 50 goes a level up? What happens?
I like this question. Does it go a level down or does it go a level up? So
what do you think, Hassib?
Yeah, for a second your Safari went away.
Yeah.
So it looks like the 50 is gonna go up. It's not like the 40 and the 60 are gonna go down. No, it's the 50, the one that is gonna get pushed upwards.
Yeah, so that's the correct answer. So the way to look at that thing is that at all times, the middle value goes to the parent, and the left of that value will become the new left child node, and the right will become the new right child node. Something like this. So 50 went up, and now it has 40 and 60. So the reason that happened is, I really wanted to point this out, how intuitive B trees are. When we did this, it automatically happened that the middle child node, which is value 40, is in between the values of 30 and 50, and the value of right child node 60 is greater than both the values of root node, and the value of left child node 20 is lesser than both the values of the root node. So since you guys have a programming assignment on this, and I know you guys are well into that, I just wanted to point this key thing out, that B trees, programming B trees is really intuitive, because you don't need to keep a track of which thing is greater than, which node is greater than the other node, since we have the conditions which are in place. So at all times, the insertion happens in a certain way. And since, like, I inserted 60, so it automatically takes care of keys of nodes getting rearranged in such a manner that at all times we have this property that values which are in the middle are in between the node values at the left are smaller, and values at the right are greater.
Yeah, so it's like so you say that when I push the 50 up, I don't need to check again if my 40 is in the right place between the children, or if my 20 is in the right place. I just push the 50, and as long as 50 is the middle of that big node that I got, everything will fit in place, and I don't need to do a lot of checking.
That's correct, with the only exception being the next case that I'm going to cover. So
Okay.
the only exception is that the case which Hassib had covered, that let's say if we have a situation where I try to insert 70, so this should go here, and I try to insert 80, this should again go here, but this causes a split. So let's go back. So let's look at this. So when I try to insert 80, it should go here. So this node will have 3 keys, hence this will split. Again, the same property that I explained, that 70, the middle value, will go up, and both the left child node and right child node will become the new left and right keys. So as you guys can see, 60 is between 50 and 70, and 80 is greater than 70, hence it is the right child node automatically, with the only problem being that now even the parent should split, because even the parent has 3 keys in it. So when you are programming this, you need to make sure that whenever there's a situation where you have 4 child nodes, so the parent will also split, and it will split in a way that 50 goes up, I'll go step back, 50 goes up, and 30 and 70 become the new left and right child node, and these 2 nodes get assigned to 30, and these 2 nodes get assigned to 70. Because even right now, if you look at it, if we do that, it becomes balanced tree, right? Because and it is keeping the property of binary search tree as well, because at all times we have a left which is smaller than this, a right which is greater than this, and so on. So this is the way insertion in B tree works, with the only exception that you guys need to really pay attention to is when the parent splits, when the root also splits.
Mhm.
So like in this case, the root has also changed, right? Because when we started with this process, we had 30 and 50 as our root values, whereas now when we are done with this process, our new root value is just 50, right? So these were the 2 really important cases of insertion in B trees I wanted to highlight, that this is how primarily insertion works. So
So
yeah.
what's the difference? Like, so the 2 cases is one where like it's a special case because it's the root, and the other case is if it splits somewhere else.
Mm-hmm. Yeah. So the other case is where let's say if we take 90 in this tree and we insert it,
Mhm.
and we take 100, we insert it. So this will fall in the category of that other case. Let me pause it. Let me step it back. So when I'm trying to insert 100, it should go in this node, the rightmost node.
Yeah.
And now, since I inserted 100, it should split because now it has 3 key values. And 90 should go up, and 80 and 100 should become the 2 new nodes. 80 will be the middle node of 70 and 90, and 100 will be the right child node for 90, right? So something like this. In this
Okay.
case, that special scenario doesn't happen because we don't have a third key value for the node containing 70 and 90. If it had a third value, like I can take an example. So let's try to do some more insertions. Let's say we insert 110.
Yeah, maybe I want to see it actually.
We do 120. And let me pause it. So since we have 3 values, now this 110 should go up. This 100 and 120 should become 2 new values like this. And since I told you guys, whenever we have a situation where we have 4 child nodes and the parent having 3 key values, it needs to split, and it needs to split in a way that 90 goes up and it has 2 new nodes, 70 and 110. And now these values will go to 70 and these values should go to 110, something like this.
Okay.
Yeah.
So it's like from what I'm getting so far is like the two cases is it's like the first one, it's like an internal split. And the other one is a split that maybe starts internal, but it gets to the root.
Exactly.
And it's like if it's an internal split, the level of the tree does not like increase. But if my split was the other case, when it gets to the root,
Yeah.
the tree will increase one level.
Yes. Yes.
Oh, so that's the two cases. Yes. Okay. Yeah. Now it's a little clearer. And then let's like right here, I can like it's easy to follow because the heap property is still here, and that's what we learned before. Where oh the left child should be less than its parent, and the right child should be more than the parent, and like especially for the like although the root has the two keys, the middle one is less than the left and is more than the left and less than the right. So yeah, and it's like you look at the tree and you can verify pretty quickly if it's a good tree or not, is just looking at the values and if it's bigger or smaller than the keys and their parents. Okay, then this is should be like really targeting the programming assignment. And it sounds like whenever we need to insert, it's like we need to double check always, or we need to check that is there those special situations that it's going to cause me to split.
Yeah.
And if it's going to cause the a node to split, how can I know which split is that? Is it like the internal split, or is it the split that's going to happen at the root that's going to cause the level of the tree to increase? So I think that's a couple thoughts that everybody should keep in mind. That when can I detect a split? And maybe this is a question, and let's maybe ask that to everybody, is like, when can we detect a split? What does everyone thinks? Let's see. Shivanku, you can't look at the chat, right? So what I'm going to do is I'm going to have you answer your answer, and I'm going to answer from the chat. And let's see who nailed it.
So what I think is the way to do it would be programmatically would be that you take a Boolean variable and you take the help of that Boolean variable in understanding whether the node that we are working on has split or not. Because there can also be a case like, for example, if I try to insert 130, this will not cause any split, right? This should easily get inserted at 120. So I need a way to communicate to my parent that, okay, I am about to split. Let's say in this case, if I try to insert 140, it will go here, but it should split. So 130 should go at 110. So I need some way of communicating to 110 that, wait, 130 is about to come into your territory. Do you have space for 130? Because if it doesn't, that's the second special case scenario we just talked about, where even that node needs to split. So I think a good idea
But
can be using a Boolean.
I think you're going a little too far with the question. I just want to detect when a node should split.
Oh, okay. When it has more than two keys.
Okay, that's good. And from the chat has like multiple ways to do it. It's the keys. Actually, no, they have one way to do it, which is your way too, is to detect that the node has 3 keys. That's when I know, oh, this is a node that I need to split.
Yeah.
What do you think another way to detect it?
If a node has 3 keys?
No, what's another way to detect a split? Let's brainstorm a little bit here. And that's the chat too. So the answer was 3 keys in a node. Okay, that you can use that to detect a split. But do you think that there could be another way to detect a split other than looking at the keys? Okay.
What do you think?
Here, well, okay, there's like two new ways come through the chat. This is really good. It's like one way is if I'm trying to insert a key to a node that has 2 keys, that means this is a node that I'm about to split. So it's kind of similar to the idea that there is 3 keys to begin with, but it's just, no, it's like a step backwards. Before I insert it and make it 3 keys, I'm going to detect that situation. That's very possible. There's also one more situation that if you have 4 children, you can know that you have to split. But it's like we have to realize something.
Yeah.
That if you're inserting at the leaf doesn't have children. So detecting that condition won't really work. If you are splitting happening internally and you have an internal node that has 3 keys, detecting 4 children to split will definitely work. Yeah, and we saw that situation in your example to begin with. You got to a point where you had a node, the root node was 4, it has 3 keys and it has 4 children.
4 children, yeah.
And that's like an indication that, oh, we could split. We could definitely split here.
Yeah.
Okay. Do you have anything else to add?
I think the only thing I want to add was that I think you and I both have given really key, crucial points which can be used in programming this assignment.
So we don't want the professor to see the video.
No, I think it's good for them, so they can watch this video again, understand it, and then use these key hints into programming the assignment.
Okay. Some people want the code. Should we do it?
No. I love my job.
All right. So in the last couple minutes, can I take the screen from you? I want to show something. Sure. I noticed there's a question, so I want to show my screen for a little bit. Okay. So one of the questions that were in the chat earlier, it was when I was talking about the efficiency and how 2-3 trees are a little bit more efficient. And it was about the number of comparisons that we do. So let's say we have this binary tree and we have this 2-3 tree. And let's say I want to insert the number. Damn, I put myself in a situation where I have to always insert a big number. Okay, let me insert 17. So the question is, or the question that came to me was, is the same comparisons going to happen in a 2-3 tree, in a binary tree, or they are not the same comparisons? And we have to pay attention to this because knowing the number of comparisons will give us an idea into the performance. If I'm doing a lot of comparisons, maybe it's not going to perform good. But if I'm doing like the minimum number of comparisons possible to get where I want in the tree, that performs a little better. So the question is, let me insert 17. And the question is, how many comparisons am I going to do in this 2-3 tree to have the 17 sit? Shivanku, you raised your hand.
Yeah, I think you can pause it and then they can see how many comparisons it's going to happen. I mean,
Okay,
pause it
fair.
and you can click next.
Okay, let's walk through it. I'm trying to insert 17. I am going to pause, insert, and let's step forward. So this is really important for everybody. This will show the performance benefits, or if there are any performance benefits or not. So 17 is going in. I compare it with the 6.
1.
That's first comparison. Then from the comparison, I know that's going to go to the right. So it goes to the right. And now, again, I'm trying to insert 17. I need to know where 17 is going to sit. But is it between the 8 and 12, or after the 12, or before the 8? So how many comparisons are we going to do here?
Just 1.
1 or 2.
Yeah.
Depending on how we do the comparisons. Because if I'm inserting 17, I compare with the 8, it's bigger than the 8. Then I go, oh, it might sit in the middle, but I still need to compare to 12. So I compare with 12, it's bigger than 12, so it sits next to the 12. Yeah. So that's 2 more comparisons. So what's the total so far?
3.
3 comparisons. And from this, to comparisons with the 8 and 12, I will know that the 17 should go to the right of the 12. Then that means I'm inserting next, like with the 15. And how many comparisons do I need to know where it's going to go? Is that right to the 15 or left to the 15?
Just 1.
Just 1. And indeed, we do 1 comparison. It sits next to the 15. So how many comparisons we did?
4.
4. So I'm going to take the 17 and I'm going to insert it in my binary tree. And let's see how many comparisons we do. 17, I'm going to pause, insert, and let's step into it. So for here, we'll make it a little easy because there's only 1 number. So every time we visit a node, we do just 1 comparison. So we can count it as like, oh, every time we visit a node, that's 1 comparison. So what's the count right now?
1.
What about this one?
2.
And it looks like the red bubble is like when it do the comparison. So we have 2 comparisons so far.
3. Yeah. 4.
That's a 4th one.
5th.
That's a 5th one.
6th.
That's a 6th one.
7th.
Yeah.
And 8th.
8 freaking comparisons to do in the binary tree. So for the question that I got asked earlier, is it going to be the same comparisons? No. And it's the reason it's not the same is because of the tree is balanced. That's the reasons we can have less comparisons. We put the 17 in the right place using 4 comparisons in the 2-3 tree. When we do it in this binary tree with our input, we need to like double the number of comparisons to do it. It's not always double, but in our case, it's double. It is the case though that on average in the 2-3 trees we do less comparisons. So that would conclude the insertion. I hope this was useful for everybody to know in the first place, why are we learning about 2-3 trees, and what's the special property about this class of tree data structures, and the benefit that we get from it. Then I also hope that everybody got a clear vision of what the different situations of insertion we have, and how can we detect a split, because that's really important when inserting. Then I think that's it for our session. We will jump into the closing remarks.
We hope that you guys could have a better understanding of 2-3 trees through this session. And I'll have my in-person sessions on Thursdays and Fridays. On Thursdays, I have my session from 3 to 3:50. It's in Peer Connections. It's in room number 602. And on Fridays, I have my sessions from 12 to 12:50, and it's in BBC Hall room 124. And what about you, Hassib?
For me, I have my in-person sessions twice a week at 5 every Monday and Wednesday. So Monday, Wednesday at 5, Sweeney Hall 411. For everybody who is trying to find out the information about the sessions, it's on Canvas. It's one of the announcements in the beginning of the semester that we made. You can always reference that information. Definitely come to the sessions. There's like you get a different feeling when it's in person, obviously. And bring any questions. Our sessions are 50 minutes. They're not technically an hour. So it's like there's just so much we can do in those sessions. And the virtual sessions are like an added benefit to everybody and for the people who cannot show up. So yeah, I look forward to seeing many of you guys in the in-person sessions. If you guys were trying to get an idea of what's happening in the in-person sessions, talk to the students in class, talk to us in class. Me and Shivanku will be in class. You get an idea for what's happening, what are we trying to cover. And we're also, to touch on the virtual session, the next virtual session will be in 2 weeks. We will be announcing the time in an announcement on Canvas, probably by next week. And meanwhile, if you guys want specific ideas to cover in our virtual sessions, shoot us an email, let us know. Our emails are on our Canvas announcements too. You guys can talk to us through the Canvas platform too if you don't want to use email. And yeah, let us know like any stuff to go over. The nice thing about the virtual sessions is sometimes we can stretch it a little bit more than an hour to cover some extra stuff. So definitely let us know. And thank you to everyone who attended. And talk about the sessions in class. Let's have some more people show up. It's always nice when we have a big crowd. The chat will be on fire, literally. Okay. Thank you, everyone. Thank you, Shivanku.
Thank you. Thank you, guys. Thanks.
Bye-bye.